Jai Hind everyone. In this lecture of the subject Electrical Machines 2 KEE 503, I am going to discuss some more numerical questions based upon three-phase induction motor 2. Based upon three-phase induction motor in this subject of Electrical Machines 2. So starting with this first question, it is a 4-pole 400 volt 3-phase induction motor has a standstill rotor EMF of 100 volt per phase and a rotor reactance of 0.5 ohm per phase. The rotor resistance of 50 milliohm per phase. Calculate the maximum torque and the slip at which it occurs. So the question is based upon the torque production and maximum torque production in three-phase induction motor. Certain parameters are given to us in the question. So let us start with what is given to us in the question. So we are having a 4-pole machine. Number of poles of the machine are 4. Motor is rated for a voltage of 400 volt. It is a 3-phase induction motor, right? Now, besides this, all the parameters which are given here are actually the parameters of the rotor, right? So, the standstill rotor EMF is given to us as 100 volt. The standstill rotor EMF is given as 100 volt per phase value, right? The rotor reactance, again at the standstill condition, the rotor reactance is given as 0.5 ohm. So, rotor reactance is 0.5 ohm. This is also the per phase value of the rotor reactance. It is at standstill condition, right? So, standstill rotor reactance is given as 0.5 ohm per phase. Besides this, the rotor resistance of 50 milliohm per phase is also given to us. So, rotor resistance of 50 milliohm per phase is also given to us. We are supposed to determine the maximum torque developed by the motor and the slip at which this torque is developed, right? So, for your reference, I have put the formula of the torque developed by the motor, the condition for the maximum torque developed in the motor, and the equation of the maximum torque developed by the motor. So, it's a simple question in which we only have to substitute the values in the equations to get the solution, right? So, starting with, let us first discuss the torque production in the machine. The torque equation given over here is actually the torque equation which is determined directly from the rotor circuit parameters in terms of the rotor circuit parameters, rotor circuit induced voltage and the rotor circuit impedance only, right? So, we know that electromagnetic torque developed in the machine is actually given as I2 square R2 by S divided by omega S. What is I2 square R2 by S? It is the air gap power PG. Air gap power PG is the power that is transferred from the stator to the rotor. So, we have got I2 square R2 by S divided by omega S. Omega S is the synchronous speed. The power transfer from stator to rotor takes place through the rotating magnetic field, and the rotating magnetic field rotates at synchronous speed. So, speed here is omega S, right? Now, knowing the equation of current I2, we can very well determine the torque developed by the motor, right? Now, one more thing, this is the per phase air gap power. If we are having an M phase machine, so I'll write this power as M times I2 square R2 by S. Otherwise, for a 3-phase machine, which is the case with us, we'll write it as thrice I2 square R2 by S, right? So getting the equation of current. Now you see over here, under normal running condition, the induced EMF is SE2S. E2S, as per this particular nomenclature, E2S is the standstill induced EMF in the rotor circuit, of course, the per phase value. So, substituting the equation of current I2, which is determined from the rotor circuit parameters only, considering the equivalent circuit of the rotor side only, the torque equation obtained is given here, right? Now, the condition to obtain the condition for maximum torque, we have to differentiate this equation with respect to the only variable which is present in the equation, and this variable is the operating slip S of the machine. So with respect to operating slip S, if you differentiate it and equate to 0, you will find the condition for maximum torque developed by the motor. It is S equals to R2 by X2S. What is X2S? X2S is the reactance at standstill condition, rotor circuit reactance per phase value at standstill condition, and R2 here is the rotor circuit resistance. Okay, so this is the condition. Now substituting this condition back to the torque equation, you can very well determine the maximum torque developed by the motor. So proceeding and simplifying the equation with the given condition of S equals to R2 by X2S, you will get the equation of maximum torque developed by the motor as thrice E2S square upon twice omega X2S, right? So what is E2S? Now let us substitute the values over here. So it is thrice E2S square. E2S is the standstill rotor circuit induced EMF per phase value. So it is 100 volt per phase value is given to us directly in the question. So thrice 100 square divided by twice, this is actually omega S, synchronous speed omega S. So twice omega S X2S, and X2S is nothing but the standstill. It is standstill rotor reactance, right? This is also given to us in the question as 0.5. So substituting the value of X2S as 0.5 ohm. Solving this, you will get the maximum torque developed by the motor. Let me put a partition over here to differentiate the parts of the question. So here we are solving it for the maximum torque developed by the motor. Of course, we have to write down the equation of omega S. So what is omega S? Omega S is the synchronous speed of rotating magnetic field in radians per second, right? The synchronous speed can be determined in RPM, in RPS, or in omega S. I mean to say in RPM, in RPS, or in radians per second. So in RPM, NS equals to 120 F by P. In RPS, this is in RPM. In RPS, NS, lowercase letter n is used over here. It can be written as twice F upon P. This is in revolutions per second, and omega S is nothing but the same speed in radians per second. So it is twice pi ns, where ns is the speed in radians per, in revolutions per second. Ns can be written as twice f upon p. So I can very well write here 2 pi into the frequency, and the frequency is not given in the question. When it is not given in the question, we assume the frequency to be 50 hertz only. So it is twice f upon p. For ns, I have to put 2 times 50 upon number of poles. Number of poles given are 4, right? So solving this, just simplifying this equation, we'll get omega s as 50 pi. This is in radians per second. So substitute this value of 50 pi in this particular equation and solve it. Solving this, you will get the maximum torque developed by the motor in Newton meters. Always remember to put the unit of the quantity calculated. Without unit, there is no significance of the quantity that we calculate while solving a question. So, if there is any doubt in this particular question, please write your doubt in the chat. Now, let us consider another question. This question is based upon the no-load and blocked rotor test that is performed on a three-phase induction motor. So, the question says a 10 kilowatt 400 volt 4-pole delta connected squirrel cage induction motor gave the following test results. Always pay attention about the connection of the motor, whether it is star connected or it is delta connected, because the solution while solving the question, first thing that you must keep in mind is whether the stator winding of the machine is star connected or it is delta connected, right? So, the motor is rated for 10 kilowatt, 400 volt and motor is wound for 4 poles. The test results so obtained are mentioned over here. The no-load test results are 400 volt, 8 ampere, 250 watt. So, 400 volt is going to be the line voltage, 8 ampere is going to be the line current and 250 watt is the total power measured under the no-load condition. Likewise, let us consider the blocked rotor test. So, the blocked rotor test data is given as 90 volt, 35 ampere, 1350 watt. So, under blocked rotor condition, the total power absorbed by the motor is given as 1350 watt, right? Besides this, DC resistance of stator winding per phase measured immediately after the blocked rotor test is 0.6 ohm. See, this is the DC resistance of the stator winding, right? While solving the question, we must have with us the AC resistance of the winding. Why there is a difference between the DC resistance and AC resistance? The answer lies in the skin effect. Because of skin effect, the AC resistance, or I must say the effective resistance offered by the wire or the conductor for the flow of AC current is the AC resistance of the winding, and the AC resistance, because of the skin effect, actually the effective resistance of the wire increases when the wire carries alternating currents, right? So, the AC resistance can be determined as, if suppose this is R1 DC, then R1, which is nothing but R1 AC, can be calculated as 1.2 times of 0.6, this much ohms. So, we have got the resistance R1, and R1 is the stator winding resistance per phase value. Calculate the rotational losses and the equivalent circuit parameters for this particular question, right? So, we know that no-load and blocked rotor tests are performed for determination of the fixed losses and variable losses in the machine and for the determination of equivalent circuit parameters of the machine. Once we have got the equivalent circuit parameters, it becomes quite easy because we have converted that machine, that physical entity, into an electrical circuit. And you know that this circuit is nothing but a series parallel RL circuit only, right? So, the analysis of the machine becomes quite easy for any condition, for any type of loading, if we have the equivalent circuit of the machine. The various parameters of the equivalent circuit are resistance R1, resistance R2, reactance X1, reactance X2 and the reactance XM. XM is the magnetizing reactance of the machine. Here in the simplified equivalent circuit, we are not considering that RC branch which takes into account the iron losses taking place into the machine, right? So, we need to calculate with the help of the no-load test and blocked rotor test data. We have to calculate the equivalent circuit parameters, and the parameters are X1 and X2, and X1 and X2 are the stator winding and rotor winding leakage reactance, and you see that the value of stator winding and rotor winding leakage reactance is given as half of XBR. What is XBR here? XBR is the blocked rotor condition reactance, and we will calculate the value of XBR from where it is calculated from the blocked rotor test data, right? Then comes the resistance R2. So we have got X1, X2 from this equation. For determination of resistance R2, it can be written as RBR minus R1, where RBR is the resistance calculated from the blocked rotor test during the blocked rotor test. Resistance calculated from the blocked rotor test data from the blocked rotor obtained from the blocked rotor test. So the equation involves RBR minus R1 X2 upon Xm, and capital X2 is defined as rotor self reactance just for the simplification of the equation, and it is the summation of X2 and Xm, where X2, this small x2 is nothing but the rotor winding leakage reactance. Xm is the magnetizing reactance. So in this particular equation, actually, in comparison with Xm, the value of X2 is quite small. So we can further simplify this particular part of the equation and we can take it equal to almost unity. In that case, with such approximation, if you are applying that approximation, then with such approximation, the resistance R2 can directly be written as RBR minus resistance R1, right? Then comes the Xm. Xm is XNL minus X1. X1 is obtained from the blocked rotor test data calculation. X1 is the stator winding leakage reactance, and XNL is the no load reactance. The no load reactance is calculated from the no load test data of the machine, right? So, starting from the blocked rotor test data, blocked rotor test. So, what we can calculate? We can very well calculate ZBR, then RBR, and knowing ZBR and RBR, we will calculate XBR as equal to ZBR square minus RBR square. Agreed? ZBR is VBR per phase value divided by RBR per phase value, right? Now, from the given test data, the voltage VBR is 90 and the machine is delta connected. So, line voltage 90 is the line voltage, and the line voltage and phase voltage are same for the delta connected stator winding. So 90 itself divided by IBR. The current during blocked rotor condition is given as 35 ampere and it is actually the line current. So for calculation of ZBR, I have to first convert this line current to the phase value of current. So RBR is 35 divided by root 3 will give me the phase value of the current, right? We know that line current is root 3 times of the phase current. For delta connection, line current is root 3 times of the phase current for delta connection. So the phase current during blocked rotor condition can be written as 35 divided by root 3. Now the RBR can be written as PBR divided by IBR square, right? So I have to take the complete I square R loss, or I have to take the per phase value of this, right? So let me take the per phase value of the power. So 1350 divided by 3 will give you the per phase value divided by the per phase current square. The per phase current is 35 divided by root 3, so square of this. So solving this, you will get the value of ZBR. Solving this, you will get the value of RBR. Then XBR can very well be calculated substituting these values in the equation of ZBR square minus RBR square. So once XBR is known to us, I can very well calculate X1 equals to X2 equals to half of XBR. There is no way of separating the reactances X1 and X2. So in general, for squirrel cage induction motor, it is taken as X1 equals to X2 equals to half of XBR, right? For certain types of the motor, the percentage may be different. Like here we are taking 50% X1, XBR's 50% is X1 and 50% is X2. So I have written X1 equals to X2 equals to half of XBR. In some of the motors like class A, class B, class C, class D, out of these motors, for some motors, the ratio can be taken as X1 is taken as 60%, that is 0.6 XBR, X2 is taken as 0.4 XBR, or in some other machine, it can be taken as X1 can be taken as 0.7 XBR, X2 can be taken as 0.3 times of XBR. So from here, from the calculations so obtained, we can very well calculate the value of reactance X1 and reactance X2. Now, let us come back here. For calculation of resistance R2, I must have Xm. So, let us first calculate the next parameter, that is Xm. We can calculate Xm. It is the same question I have taken on the second sheet as well for the solution purpose. For the calculation of Xm, I have to use the no load test data. Using the no load test data, I'll calculate ZNL, I'll calculate RNL, and knowing ZNL and RNL, likewise what we did for the blocked rotor, from the blocked rotor test data, we can calculate ZNL, we can calculate RNL, and knowing these two, I can calculate XNL equals to under root ZNL square minus RNL square. Agreed? Knowing XNL and knowing the reactance X1, I can very well calculate Xm equals to XNL minus X1. So, when you will solve the equation by substituting the values, you can very well calculate the Xm. Knowing Xm, I'll proceed for calculation of this capital X2 or for solution of this particular equation. This equation can also be written as R2 equals to RBR minus R1, and here it is X2 small x2 plus Xm divided by Xm. So knowing the value of Xm from here, I can very well calculate the value of resistance R2, right? Now besides these, in this question, I also need to calculate the rotational losses of the machine. So what about the rotational losses of the machine? The rotational losses of the machine are actually calculated from the no load test data. But what happens during no load test data, some I square R losses are also taking place into the system. What is the reason? The reason behind this is the no load current of three-phase induction motor is quite high. It is 30 to 50% of its full load current, right? So we cannot neglect the amount of I square R losses taking place at the condition of no load test, under the no load operating condition of the machine. So for determination of the rotational losses, what I have to do, I have to subtract the no load I square R losses from the machine, right? M is for the number of phases. For our system, the number of phases are 3. PNL is the total power measured under the no load condition. It is given to us as 250 watt, and this is per phase I square R losses under no load condition. So the no load current is 8 ampere. It is the line value of current. The per phase current would be 8 divided by root 3. So INL square multiplied by resistance R1. R1 is calculated here. It is 1.2 into 0.6. So just substitute the value 1.2 into 0.6. This will give you the total rotational losses taking place in the machine under no load condition. So that is all for this lecture. We will proceed with some more numericals in the next video of this subject. Thank you.